Okay, so we have the LM399 based precision power supply that is being heated by this temperature controller, and then there's a heat sink and a heat plate on the inside, temperature monitor or sensor. One of the main reasons why this temperature compensation is really so important to me is that I live up here in the mountains and we get some dramatic temperature changes, especially into the cold. But it's nothing for this shop to change 10 or 15 degrees, even though I keep it heated overnight. So being able to withstand a 10-degree change without significantly changing my calibration on this unit was important to me. So that's why I'm giving this thing a real good try. I've targeted the temperature to be well above the mean temperature of what we have up here. So anyway, it's maintaining 30.2 degrees. It actually fluctuates between about 25.6 to about 33, but the average is probably more like 30.2 or 3 degrees. And we're monitoring right now the output of this Decadivider RV622. It's a 6-decade divider. We're looking at the output. We're set to 9999910. So in this case, we should be seeing essentially the input, and we can check that. Okay, we're getting an input of 10, all zeros. And we go back to the output of this thing and take another look. And we got 10 all zeros, and we might see an occasional flash to a 9. There is a very minimal loss in this thing somewhere, but it's, I believe, within specs. So what we're going to do, we're going to dial this thing down. Like right now, I'm going to go to an 8. And we see that we've got 9 and all zeros. Well, that's because we got 10 on the last digit. Let's make that a 9. Now we got 8 and all 9s. That's easy to see. Let's keep it that way. We go to 7. 7.9999, or 7. Now there is an error allowed for every step, so if you don't see a perfect 9 at the end, I'm not worried about it. That error is small compared to the largeness of the number itself. So 6 4 9s and a 6. Go to 5. 5 4 9s and a 5 or a 6. 4 4 9s and a 7, 6 or a 7. A 3 4 9s, 7 or 8. 2 all 9s. 1. Got a 2 and all zeros to a 1. And then we'll make the first digit 0. We've got 1 and 4 zeros and a 2 or a 3. Alright, now we'll take the first, this is the first decimal place. We're going to go from a 9 to an 8. And we see that we drop to a 0.90023. If I go back up a step, we're at 1. So we see we came down a 10th. Let's go down another one. There's 8,000,30. I dialed in a 6, we get a 7,000,30. Dialed in a 5, we get a 6,000,34. A 4, we get a 5,000,39. Dialed in a 3, we got a 4,000,42. Show you what I'm doing. Dialed in a 2. Got a 3,000,47, dialed in a 1. Got a 0.20015, dialed in a 0. We got a 0.1001718. Make it an 18. Okay, so we should be reading 0.09999. We're getting 0.10000 17 or 18. So we're going to dial in an 8 on the second decimal place. And we just changed our scale automatically. We're 90.012 millivolts. And that would make sense because we were reading 89.99, 90. Let's go to a 7. Excuse me. We'll edit that out. At a 7, we're reading 80.010. 6. 70.006. Probably 6 average. We're at dialed in a 5. We've got 60.0038. Dialed in a 4. We got 50.002 something. Dialed in a 3. We got 39.9995. Dialed in a 2. We got 29.9996. Dialed in a 1, we got 19.9995. Now the second decimal place is 0, and we're on the third decimal place. We got 9.992, 8.992, going to a 7.992, 6.992, 5.992, 4.992, 3.99, make it 3, 2.993, 1.993. Now the third decimal place is a 0. We're down to the last 2 9s. All right, we're going from 9 to an 8. So we've got 0.893, I don't know, 7 maybe. 0.8937 millivolts. And we've got 89 showing on the dial, so we got the 89 showing. 7, we got 79.38, 69.37, 59.37, 49.38, 39.38, 29.39, or 19.39. Now the fourth decimal place is 0, and we're down to the fifth decimal place. We got 9, 8, 7, 6, 5, 4, 3, 2, 1, and 0. We've got a residual of 3.8 millivolts. Or excuse me, 0.0038 millivolts, which would be what, 3.8 microvolts? What if I nulled that? Yeah, we could. Go back up to a 1, 2, 3, 4, 5, 6. It's pretty exciting because you can actually, you got complete control over the number. What if I make this just for kicks? Let's do a 9, 8, 7, 6, 5, 4. 9, 8, 7, 6, 5, 4. That's pretty amazing. Nine, 8, 7, 6, 5, 4. Dialed it in. Got it. Wow. Let's do 9 and all 5s. 9 and all 5s. Hi, it's Bruce, and welcome to my Rocky Mountain lab. And as you can see, I'm in the process of doing something here that's an extenuation of what I did earlier. This is my precision 10 volt, I think it's an LM399 based precision reference. I have it temperature controlled. Inside we have a ceramic plate that's heating a heat sink, which heats the board. The interior is insulated, and we're taking the output, feeding that to a divider, and then taking the divider and measuring it. Right now I should be getting basically the same as the input on the output. And what I see I'm getting is 10 and 5 zeros with an occasional blip to 10 microvolts at the end. And what I found, this has been running now for about a week, and I find that the majority of the time I'm at 10.5 zeros. I do have a blip to the 10 microvolt level that happens after the heat is applied to the heat sink, and then she cools off, and then she gets down to the level where it needs to kick back in again and reheat the plate, and at that point we basically are all nines. So I'm seeing a plus or minus 10 microvolt change in voltage due to temperature. And I'm already I'm adjusted about as fine as I can be adjusted on this. We are right now at 29.2 volts for the trigger point and 29.2 volts for the removal of the voltage from the heat plate. So at first you might say, well, what good is that? Because you're starting and stopping at the same temperature. Well, the fact is, it triggers at 29.2 volts, or 29.2 degrees centigrade, and but the temperature falls a little bit, and it takes a moment or two for the heat plate to heat up the sensor enough that the sensor sees 29.2 degrees centigrade and shuts off. By that time, there's enough heat absorbed into the heating plate that gets imparted to the heat sink and then eventually makes it to the board, that the temperature swings as much as 3 degrees centigrade, quickly falls until it hits about 30 degrees C, and then she kind of holds pretty nicely as you get a 10 and 5 zeros at that point, as you can see on my meter. And eventually it cools off, gets down into the all nines, and then kicks back on again. So just by watching this thing, I'm centered about where I want to be. I'm between all nines and 10 with all zeros and an occasional blip to a 1. I'd like to be able to make the temperature control finer in this box. The only way I could do that was to order another heating plate. And the heating plate I ordered, it's a 220 volt heating plate instead of a 110. It'll still work off a 110, I'm certain. It will provide less heat at 110 than it would at 220. Plus the output of the plate was like 5 watts instead of 30 watts, which is what I have in there now. So what should happen is that I should be able to more widely open the space between the reheat trigger point and the off point and heat up that plate more. It'll provide less heat even at maximum, and we should be able to somewhat control to a much finer detail the amount of heat that's applied to the board. That's the hope. I'll find out when we get the heat plate and I can make the difference, and we'll get back together at that point. Okay, so I received my new hot plate for my temperature controller. This is the one that I had before I took out. This was 110 volt, 230 degrees centigrade, 30 watt hot plate. And I used to cycle that with the turn on and turn off temperature basically right on top of each other, so that this would only pulse, get really hot, dissipate through a big heat sink in this unit and create a temperature change, and then it would come back down and then repulse again. And I got close. It did a pretty decent job, but I was varying about 10 microvolts over time, so I wanted to try and solve that problem. So what I did is I got a new hot plate. The new one is a 220 volt 3 watt 60 degrees centigrade. So it's all the way around. It's dramatically decreased from what this was. So the amount of energy that I'm putting into the heat sink with each pulse is dramatically lower. This would mean that my cycle time would probably be shorter, but I would be able to more finely tune in my end temperatures, the thought I had anyway. So this thing's been on now for 24 hours, and I am producing a pretty stable 10.00000 voltage. We see a little fluctuation there between all 9s and the 10. We're right on the border of the 10, so that's not bad. I suppose if I could bring myself to keep that 10 at a very stable position, I'd be even happier, and I might try and adjust the temperature a bit to do that, but right now I'm pretty happy. This has been going on. I haven't seen anything other than all 9s and a 10 for the last couple of hours since I made my last adjustment. The other thing I did was I replaced the insulating material that was inside the box. I had used some packing foam that I'd had as an insulation material, but I ran across aerogel blanket, and the aerogel blanket, I read about it, it's space age material, supposedly has the highest R value that you can get, and I figured I'd give it a try. It was a small amount, so the $11 or $12 it cost me for the insulating material, I just figured, big deal. What I did find out was that it's very difficult to work with, in my opinion anyway. Very dirty too. It's the dust that comes out of that thing it's just got everywhere. I had to clean this shop up for about an hour afterwards. But I did finally get it all in here, and was able to pierce the material and feed my wires through and everything. So I'm better insulated, I believe, than I was, which was something that I wanted to do. I figured if I could improve the insulation, that would help slow down the loss of heat out of the box and slow down my whole heat cycle process. So that's kind of the update as to where I am. I'm going to keep an eye on this thing for another week or so and just sort of see how I'm doing. We can see right now that we're doing pretty good. We're holding a very steady 10. All 9s to a 10. That's just the way it's been. I decided that I really wanted to try and decrease the amount of heat coming out of that hot plate even more than what I got by just installing the new plate. And I thought about inserting a resistor in series with the heat plate, dissipating part of the power, and therefore lowering the amount of power that the heat plate got and would heat up with. And then it hit me that maybe an even better way would be to insert a diode into one of the leads of the hot plate, and therefore rectify the AC power and provide the DC equivalent for half of the cycle. So effectively, I've cut half of the power out of the hot plate. And in doing so, the length of time that the unit senses the temperature change between the point where you want to come back on and the point where you want to come off has increased 2 or 3 times. It's now a matter of a couple of seconds versus a split second. And it gives the electronics, the thermistor and so on that's sensing the temperature in here, a chance to react much faster than it could before, much more accurately. So the amount of energy that I'm delivering to the heatsink can be controlled more tightly. And I've done that. So I am seeing a better response out of this thing, and a little bit tighter control of my voltage change on the output. So, okay, so what I've done is I've gone ahead and I've set the temperature so that we come on again at 31.5 degrees centigrade, and we go off at 31.5. Physically, what happens is we'll hit the 31.5 degrees centigrade, but it'll typically go another tenth lower before it's able to warm itself up enough to where it senses that it's hit 31.5 degrees on the output. So we're warming up the hot plate for a while, and then it senses the 31.5 degrees has been achieved, shuts off, and then the heat from the hot plate gets delivered more fully over the next several minutes to the heatsink, which delivers it to the board, which warms up the chips and affects the voltage. And what we found here, or what I've found, is that I have less interference from the room temperature, and if by chance room temperature was enough to overcome the set point, I would have no way to cool this thing down again. So I would lose control at that point. By raising the temperature up into around 90 degrees, which is a temperature we would not likely see up here at 9,000 some odd feet, 9,300 roughly, then I am able to control it using my controller and hot plate. So we're going to see how this works. We'll do a demonstration here for a couple of cycles coming up. Well, as you can see, I've got my HP back in the frame on my workbench, and I've got a new 25-foot RS-232 straight-through cable that goes from the back of that unit, goes around the corner of the room, follows along the floor, and makes its way over to this computer where I've got the null modem connected and connected to RS-232 on one side and to the USB port on the other. So I am now nicely connected, and well, this is where I am right now. We are running 31 degrees at the heat point, and 31.1 degrees at the cutoff point. And last couple of cycles, that has put us right around the just a little bit less than 10 volt. We'll say about 10 would be what, 9 point, probably 5 nines and an 8, somewhere in there would be the average. It looks like it may have warmed up just a little bit more, and so the average is going to be a little higher this time. But the result is we are getting 10 volts on the meter with 5 zeros, and until the lower end of the cool-off period, it doesn't change, at least it hasn't, until we start to hit the 4 nines and a 5 in the decimal place, and at that point I start to drop into all nines. It doesn't happen much. There's several times that I see it here on this graph. So the point to that would be, I would when I see myself starting to change, I will take the higher of the two numbers, at least for now. Here you can see on the computer screen what the voltages are running. There's 6 nines and a 4, 5 zeros and a 1, 5 nines and a 7. Yeah, you got that noise that fluctuates in there. Basically, I'm happy with it. There are some things about the board that I am not happy with. It has a really bad hysteresis when you're trying to adjust the pot to get to exactly 10 with, say, 5 zeros. You will find that it's very difficult to get to the 10, and about the time that you should get to it, it will suddenly snap, and you'll either go 10 or 20 microvolts low or high, depending on which direction you're going. It's just a really bad hysteresis. And as a result, I found myself having to depend on utilizing the temperature as a means of fine-tuning my in point. So I adjust my my pot very carefully to try and get me to where I want to be with my temperature, say, centered around 31 degrees right now, centigrade. And then I fine-tune it using the 1/10 of a degree centigrade adjustment up or down to move my line up or down. And that's been successful for the most part. But even here, I've experienced some oddities. Every now and then I see spikes I can't explain. Like here's some negative spikes that are, maybe 20. Let me see. That's 1, 2, 3, 4, 5. All right, so that's let's say that's 2 to 3 microvolts. Suddenly we spike negative. Why did that happen? It wasn't happening, all along here, and then all of a sudden you had a few of them that are just weirdly weird. Don't know what to make of that. And I've also seen where over long periods of time, this thing just suddenly shifts. The line will make a very sudden shift, 1 or 2 or 3 microvolts, one direction or the other. So stability seems to be an issue, and I'm just going to have to keep working on it to figure it out. Right now, I see a spike where I'm going over the 10.5 zeros and a 5. That's going to give me a 1. That's going to take my last zero. Instead of having 5 zeros, I'll have a 1 there. I don't want that. I've been trying to keep below that point. So you kind of get the idea. But if I could do it, I'd love to change that pot for a lower value. I mean, it's a 1 kilo ohm pot. I probably would try and go for like a 250 ohm pot and just make my resistors on either side a little larger. I think you've got more than enough play in that pot to compensate for the voltage. I find that it's a very small change, makes a very great change in voltage. Very small change in the pot position, very great change in voltage. Okay, well, thank you for listening and putting up with me. We'll see you again another time.